Hi there. Today we're going to look at this paper called Scene Transformer, a unified architecture for predicting multiple agent trajectories, published on the 6th of October 2021, published by the co-first authors Joachim Nguyen, Benjamin Kane, and Vijay Vasudevan from Google Brain. Looking quickly through the abstract, they will present their technique, how to predict motion of multiple agents within dynamic environments. Dynamic here means, for example, road objects like traffic signs can have time-dependent states, but also the normal case that each agent, like a vehicle or a pedestrian, has different time-dependent states. They say that in prior work that the future is typically predicted for each agent independently, and they claim that this led to suboptimal planning prediction. In their work, they use a model for predicting the behavior for all agents jointly, with a consistent future and taking into account interactions between the agents. Inspired by the language models, which we see currently heavily used in the academia, they can query the model to predict agents' behavior in many ways, depending on a so-called masking strategy they apply to the model. What that means we will see later in particular. They use also an attention mechanism to be able to use features from agents like pedestrians and vehicles on the road, but also attend on road elements and all their mutual interactions at different time steps. They also evaluate their approach on the typical self-driving car datasets for the typical tasks like marginal and joint motion prediction. And they claim to achieve state-of-the-art performance on them. Good. Having that said, what does this all mean in particular? Okay, let's start with an overview. So, we typically have for motion prediction in traffic situation the following setup or the following information as sketched here. So it starts all with a environment where we have different agents. So let's take this brush here. We have like one agent here. He has potentially the option to drive that direction, or he has to drive that direction. But there are also other agents. For example, this agent here on top, he also has, or this car has also the option to drive forward or goes to the left. Also here we have another vehicle which has a green sign in here, and this also has its own possibilities to drive, so he can go to the right or he can go straight forward. These cars here on the left, they see a red sign, so they typically, or they should just stay and wait here. In the case of a marginal prediction, you choose one agent where you want to predict its possible futures. So in this case, it's this car here in turquoise, and the predictor says like, okay, I predict with this likelihood of 0.7 that the car will move on and has to stay here. Why does he has to stay here? Because there's a car which moves straightforward here, so he cannot drive there, so he has to wait. But there's also the other possibility. The predictor says something like 0.3, that the car can actually just move on, because the car on the from the top can also turn left and change the road. So that is marginal prediction. And you may see here the downsides of this marginal prediction, because all the other interactions by the other agents are somewhat implicit. So let's take the rubber and remove that. So we see here that the prediction, the future of the other agents, they are just here encoded implicitly. So I just can see here from my trajectory of that agent that he has these possibilities, but implicitly behind the scene, the model has somehow modeled that the top car is moving forward or bends to the left. And that car also has to model somehow how maybe these cars are behaving. And that brings us now to the strength of the joint prediction. Looking now at this diagram, we can see now color-coded that we have, let's zoom in a little bit more, that we have for different scenes or possible futures, a joint prediction. So we know in the blue case that this car is moving into that direction, this car is moving into that direction, and that car has to go that direction, because only in these situations, in this interaction schema, there won't be an accident. There's also another future where we can see that one other possible future would be the orange one, where, let's remove this, where the top car just propagates through, and this car has to stay here, and maybe that car also just stays here. And for the joint prediction, what we get is like a probability or likelihood for these different scenarios, 0.3 or 0.7. Okay, moving on. Again, the term scene-centric representation for all agents means that they represent the whole thing or use all agents at the same time. Do not focus just on one agent. They claim to be computational efficient, uniform, and scalable. They are inspired by language models, and that they can solve like marginal or interactive predictions or goal condition predictions as well. Having that said, and yada yada yada, going through the novelties, we should just jump in how that everything works. Now in this figure they show the main part of the paper. On the left side we see here the different so-called masking strategies, which then define the different tasks. Okay, let's start with that. So we have here the time axis, so time step 0, 1, 2, 3, 4. And on that axis we have the different agents. So agent 1, agent 2, agent 3, agent 4, and agent 5. And we have then kind of into that direction, we kind of have like channels or features, whatever. And so an agent propagates over time and has maybe different positions. So in each of this cell, you can kind of think, okay, in there I have like my position, my velocity, my orientation and stuff. And the motion prediction task looks like that I have like three consecutive measurements or representations of my world. I know where my agent 1 was, 2, 3, 4, and 5. And now I just would like to predict what is the state at that time step of that time step. For the conditional motion prediction, one can ask like, okay, maybe I have like one focused agent here in this column, and I kind of know where I will be in the future. So I know where I will be here and here. And now I just try to predict what are actually the other agents doing. What will they do? So in gray means like the gray features here mean hidden and not to be predicted by the model. There's the other one, like goal conditioned motion prediction, where maybe this is again, maybe it's me or the car in which you are in, or the car you would like to plan or to control in the future. And you know you have been at time step T1 here and at time step T2 there, but you have no idea what you will do in the future, but you know where you want to be at a particular time step. So you gray out these two cells and you gray out all the rest of all the other agents. And if you just hide these fields from the model and ask him to predict them, then you might get a consistent prediction or solution for your problem. The question is now, how do we achieve this? For that, we go to the right side where we can see the architecture, the transformer-based architecture or attention-based architecture. So they start with the agent's features at that point. So they just say, okay, now we have these agent features. So what does that mean? Let me zoom in a little bit. They start with, okay, I have like something around like 120 agents. I would like to handle 90 different time steps, and my feature dimensionality to get like enough room for feature aggregation, they use something like 256. And what they do in the first step, that they aggregate for each agent at each time step these features. So they encode here with dense layer in this feature vector informations like X, Y, and Z information, velocity, and orientation. And the block will then look something like that. So they will have here this feature block like that. Maybe that's a little bit too thick. Oops. Maybe that's a little bit too thick. So something like that. That's the feature block. Where we have here in this dimension the time step T, and here the amount of agents, and in this dimension we have the feature channel D. So like that. Good. And they first of all try to kind of do self-attention across time. That means they try to use a transformer or attention mechanism to have for each agent. So one agent could look something like that. We have here a agent which is in that block here, and they try to attend like across all these different time steps, so that one agent, so for example agent number, so if here we start with 1, then this might be something like agent number 50, that this agent has all its information across itself across time. So at that time step, for example 60, it has the information from all its other time steps and also from the possible future in case. And this is now applied again across all or repeated for all for all agents. So we can maybe look at this something like that. We have so I just reduce it by one dimension to make it simpler. So we have like time step t here and the feature channel length d, and we have here these feature tokens, how we kind of know them from neural language processing. And after the self-attention, where they kind of use a query, a key, and a value, we get out with this query and that key. We get here an attention matrix with which we can attend onto the values. And what we get out then is like another matrix which has like again the same shape with time step t and d here, and this so each feature vector or each token kind of has attention or has information about all the other time steps. So again here it has information in here and each other as well. Okay, so but we repeat this thing, this whole thing, we repeat this for all agents. So if we stay in the upper 3D feature block, then we do like attention across this dimension for every agent. Then what they do is then self-attention across the agents. That means let me draw this. So we have the first step across time. That means we have here a block like that, and so we stay with the same dimensions. Here again, here we have this here like that. And now what they do is like they apply now attention. So what did we achieve until now here? So if we stay here with one agent, so agent number 50 at time step 60, then what we have here is like a feature vector into this dimension here, like into the back. which has information about all the other time steps. And now what they apply is like attention across all the agents. Instead of going now from left to right, they stay with one time step, for example 60, and they apply attention across this dimension. So we get information from all the other agents into that. And we stay again with the same shape after that. And now the trick about that is, let me just finish this here. So the trick about this is that since, for example, this agent 50 has information about itself overall time step, the same trick holds for agent number 20, for example, here. So he also got kind of in this time step here all information about itself. So that if we now apply attention across all agents, that we kind of have achieved self-attention across all dimensions, time and agents. That means if we now look at our example, so we have like agent number 50 here at time step 60, it's somewhere in here. So that's the feature vector in here. Then it has like all information from all different agents, and each agent had information about themselves over the whole time. So what we just achieved here is like a very rich feature vector and attention across all dimensions. To get even richer attention mechanisms, to get even richer feature vectors, they repeat this attention across time and agent 3 times. And just in case you didn't get the point with the attention matrix and the query and the key and the value, I will post a link in the description below where you can go into deeper that topic. So what did we achieve so far? If we now zoom out in our architecture diagram, then we just went from our initial features from each agent at each time step. We have now here until here all information across agents and time. Now they claim here to add an extra agent and time dimension into which I will go into deeper later because this we have to handle separately. Now, since the agent features do not have any information about the environment and the road and traffic elements, they apply something so-called cross-attention towards road graph elements. So road graph or elements about the road are something like traffic signs. A traffic sign can have different states. So here again they have this 3D block. So let's take this feature block like that. We have again here the different time steps T. We have different road elements, so traffic lights or traffic lines. And traffic lights, for example, could have also a state which is state dependent. For example, a traffic light could be green, orange, or red. And again, they have here the feature dimension D. And this now gets somehow incorporated so that our agents can do attention to what they need to know about the road graph. Okay, how does this cross attention now work so that we can incorporate information from the road graph into the agent feature vectors across different time steps? Okay, let's have a look into this cross attention mechanism. We again start with these feature blocks. So we have here one for the road graph and one block for the agents at different time steps. So we have here again this block where we have like G road elements. They can be something like 20,000. So we have there a lot of them. We have different time step T, so the same like 90. And here we have the feature dimension D. For the agents, we have here, for example, 120 agents. We have T time steps and a feature vector of D. Both Ds are now the same here. They have like 256. Okay. So our goal is at the end. The goal is to have at the end a feature vector. For example, we have here the agents A at that dimension and the feature vector D, such that each agent knows or has here feature encoded about the road graph. So each agent knows at a particular time step, oh, there's a traffic sign, here are some lines, here are other shields, traffic signs, and so on. So, and how do we now get this? How do we come from these information encoded here in this feature block and the agent informations across time and all agents to that point? Therefore, we do this so-called cross-attention mechanism. It starts with the following. So the formula, which is well known, looks like that. We have attention, ATT, looks like it's the softmax, SM, about the query and the key transposed, normalized by a dimensionality factor, multiplied with the value. And now I'm going to draw it, how this will look like in our case. So we kind of now, we have to drop the dimensionality, not drop, but we choose now one particular time step. Therefore, I have to draw another. So we now choose one time step. So let's say we have here T at T1. We have the features of our agents A and the feature dimensionality, the feature here. So each agent has here has its feature vector. And we're going to use this after we put that into a linear layer, into a dense layer. We're going to use this as our query. So this will be our query. I think they normally just put here like that's our query. Then we need our key. So we do the same here for the road graph. So we have here, maybe one step to the right, like that. We have here our G elements, so these traffic signs. Also for one time step T1, that means we have for all elements at one time step. So we have different traffic signs, we have different traffic lights, we have road lines information all in here, and each of these elements has also a feature vector. So in there encoded is like position, one hot encoded maybe what kind of type of element it is, and somehow maybe also mixed up with the dense layer. So now we have this feature vector D, and we first of all create now this attention matrix here. So here, so that we create with a matrix multiplication, we create maybe a little more space here. So we also have to put it here into a dense layer, and then we multiply them together such that we have here again a vector with the dimension of g times number of agents. And again, I just want to repeat here, we stay here with time step t1. And this attention matrix now has information about, so if we have here like different road elements, and we have here different agents at one time step, maybe just as an example, one agent can have like, it says, maybe this one here, this particular road graph element here is, for example, a traffic sign which is right in front of me of this agent, and at the time step t1 it's red. So that means we get here a very high value for that element, for that agent, because it has really, also it needs to attend to that, because it has, for example, because it's red, it has to stay. And with this attention matrix, we're gonna multiply it with the value matrix. So again, here we have, we get, so that's here, that's there. We have, again here, so if that's the query, then this was the key, and this is the value matrix. Then, or maybe we write it here, it's even better, I guess. Key value. We also have here the dimension of G and D, and we're gonna multiply this with that attention matrix, so that we can pick out with the attention what kind of information we're gonna need from that road graph. So we have here again the features of each road graph, and here is the attention. But we also have to do some certain normalization. That's why they do this softmax. So in between here, they scale it, and they also put here a softmax, so that these things get normalized. So if they apply this this matrix G times D, or D times G, and the matrix here A times G, we somehow with the proper transpose, if we transpose it correctly, we can get here this new matrix of the dimension D times A. We got rid of the dimension G, but we have incorporated for each agent at a particular time step T1 that each agent has now in its feature vector information about the road graph. Yeah, so, and that was that part here, that we do cross attention agents to the road graph. So we just picked out here just one time step, and this will then of course happen in parallel with all the other time steps. So maybe at time step T1, the agent, for example, that agent here has incorporated that the traffic light in front of it is red at time step t1, but then at time step t3, it has incorporated that the traffic light is changed the color. Good. So, cross attention. We have now information from the road graph in the agent feature at all time steps. Now, we again apply self-attention across time now. So we just go back and we apply the same mechanism that we go again, go through time. Let me change my brush. So we again go, we have now the feature vector of each agent here. Let me change to another one like that. We have here each agent, each feature vector has information about the road, and now we attend over time for each agent. That means an agent now gets information over itself and over the situations over time. So it knows at a certain point, okay, in the past I had red traffic sign, red traffic light, red, 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 and then at a certain point it is then green. So that's why they do like self-attention across time. And after that, again, self-attention across agents. So we go again back here. So each agent knows something about itself, about its all time steps, and now we do no incorporation between the agents for a particular time step. So for example, even though I know that I can now drive, it's green maybe, but I also have to take care what are all the other agents doing. Okay. The whole procedure gets here repeated. So we have here cross attention agents to road graph. So we just repeat that process, that we again can get information from the road graph to foster that, and we repeat the self-attention for time and agents here again. And the output is here the agent features of the dimensionality A. I skip now the +1, I come to that later, T and D. And this is essentially the attention-based encoder block we have just seen here. Now the next step will be to look into the attention-based decoder block, where we just start with the agent features and have at the end a feature or an output for all agents A, for different time step T, for different regression values, which are 7 in that case, and for F different possible futures. So the 7 is X, Y, and Z and their corresponding uncertainty, and the 7th regression value, is the heading of the vehicle. Okay, now we do one step back. Now we have seen kind of the whole architecture. We go later in detail a little bit more, but we just do now one step back because I would like to explain now why we have this extra dimension here, this +1 everywhere, why this is actually needed. So the main purpose for that is that we kind of try to predict for 2 different tasks. We have seen at the beginning that there are two different possibilities how we can predict the future. So I just remove that part here. So we have this marginal prediction. This marginal prediction means that we can predict the possible future for one agent, now this agent here, where we say most probably we think that he will just stay here, and the other future would be that he goes like that. So here implicitly encoded is how all the others would behave. So why we do that? There are use cases where we want to have this information, but also the benchmarks are kind of created that we need to predict for one agent the possible futures. In more like interaction benchmarks, we have this joint prediction where we have one scenario. So it's a blue scenario where this car goes here, that car goes there, and this vehicle turns to the right. And there's the other situation where we have the orange case. So the orange case goes like that. This car goes here, that one stays here, and that one also kind of breaks here. And to be able to predict these probabilities for these different tasks and different futures, they kind of use a trick to add this extra dimension here. So they say here, add extra agent time dimension. So let's go back to this diagram here on the right side, where we have here on this axis here the time, and on that axis the agent. And if we see it like this, if we go across time for one agent, so we have like this one agent we would like to predict for the marginal prediction, then we say, okay, at time step 1, this agent is here, then it's there, then it's here, and then I have to predict where it will be here and when it will be there, or where it will be. So what they do is here, they also like add here one extra dimension for that agent, where they put in here the probability for that agent. And since one agent can have multiple futures, there's also then this future dimension here extra. So we have in here like F for an extra future. And we have another dimension, the fourth dimension, which we always use, is the feature dimension D. But this I will just want to use here in the explanation. Good. So we have, this is kind of for the marginal kind of representation. But we also see here that, so this is like why we have this agent plus one dimension. Oh no, sorry, it's actually the T plus one dimension. So we add here an extra dimension for time step T. Now they also add for an extra agent dimension. And now you can think of, okay, I have multiple agents. Let's just pick me another color. So we have like agent 1. We have agent 1 here, agent 2 here, agent 3, 4, and 5 at a given time step. And now we would like to estimate the future. Where will they be? So they have here different locations. And we would also like to give a probability for that joint future of all these agents. So we put in here another vector, another scalar, or another field where we have space for this kind of information. So we have like a joint future across all agents, and we can kind of put here extra information for that. And the same holds here for the future dimension. So we have then in this dimension also for different joint futures also different probabilities. They add this extra dimension quite early. It makes somewhat sense because that we have this normally we have this dimension of t and agents, and actually one can say that each dimension is somehow correlated to one time step and one agent, and we cannot encode there. We don't have a space, an extra space for the for the probability, so that's why they add there an extra dimension to all of that. They could have added just another channel in here, but this would make it more difficult to process with these transformers and attentions. That's why there's this trick to just add there another pseudo agent and time step. They also argue that then there's more space for more richer features, or that there's a placeholder where you can store that kind of information. So we have then this extra feature here, here, and here, also there. Also in the decoder block, we also have it in here. And they use it also in the decoder block where they do this self-attention across time and agents 2 times. And here, right before the end, they slice out the extra agent time dimension. So they take that out, and then they use these channels, or these extra channels, these features for a separate task for predicting the probability of a given joint future, or a given marginal future of an agent. Now I would like to go into detail how they add this extra dimension of f possible futures. The main idea here is that they just take this agent feature block and they just tile it. They just copy that block f times. For f, they kind of use I think 6 possible futures, and they just copy it. But what is not here? So they tile it. And in between, they add some extra features here, which I have to zoom in. Okay, for this D dimension here, they do a step which is not directly, which you cannot directly see here. So this tile operation again makes this just duplicates the whole block of features. It just copies it. But then they have here this MLP step. That means they have for each future f, they have this D dimension, and they just concatenate here another feature vector of length f, so for futures, and then they put here a1 into it. And now comes the part where I'm not fully sure how they are actually doing it, so I would like to just read the part together with you. So now we are here in the appendix, and they make some comments on the decoding of multiple futures here. So in order to allow the decoder to output f futures, we perform the following operations. The decoder receives as input a tensor of shape ATD, corresponding to A agents across T time steps and D features. The following series of simple operations restructures the representation to predict F futures. First, the representation is copied across F dimensions to generate F. So they copy ATD F times. Then, now comes the tricky part. We append on a one-hot encoding to the final dimension where a 1 indicates which of the F futures is the ground truth trajectory resulting in a tensor of shape F, a T, and the last dimension D plus F. And then they claim or say the one-hot encoding allows the network to learn an embedding for each of the F futures. So I read it like that. Also, what would make sense to me is that they just add for each of these F dimensions, they have here this D vector, and then they add a 1 here vector, the others are 0, depending on which future I am. This would make sense for me, but it reads as if they keep the 1 for all futures at the same place. I'm not sure if I'm wrong here. Please feel free to comment in the section below, or maybe the authors can maybe do some comments in here as well. So, and then it goes on. For computational simplicity, the resulting representation is propagated through a small MLP to produce a return tensor of shape FATD. So they go from this 2D dimension, this D plus F dimension to this D dimension. Back. Okay, going back to our last place here. So not going into detail too much. The next most interesting thing now would be to understand how they produce a loss to the whole thing. Because you have to understand that these data sets only have just one possible future, namely the future which has been recorded by the system. So that means even though I try to predict here 6 futures, F, there's only just one future we have as ground truth data. And they say that they only back propagate through the future which comes closest to the ground truth future, while the rest is kind of ignored. But you may ask, okay, but how is it then possible to have then all the other futures? I mean, over the time, you may think of, okay, the network kind of learns to also predict other futures, but they do not need necessarily data for it, because the signal is enough to back propagate just through one future, while the rest still predicts something, and it may be also consistent, but over the time it averages that the different futures have somehow they bring some future which make sense over the time. Another last thing why this whole paper is quite amazing to me is that they can treat multiple tasks at the same time. So if we look at that figure again, we can kind of predict different futures for different things, and we can also mask out things. So as we can see here, we can ask our model to predict this kind of block here, to predict all common futures. But we also can just say, okay, I can say that I will drive this way, what will be the result, the resulting behavior of the other agents. Or you can say something like, okay, I would like to be in that time step at that place in the future. How do I have to behave to get there, and how will all the others behave during that time over different futures? And now comes another trick, that at the beginning you can also just mask out certain, so gray out actually, let me get the gray part. So you can gray out certain information, so that you do not give the CNN information about a certain, under the CNN, the detector, the transformer information about a certain agent at a certain time. And he still has to predict somewhat a consistent future for it. And that's why it's so important to keep this whole time, this dimension fixed over the whole time, so that we can have, that we can mask things out in at the beginning, and then ask the detector to predict a certain future for that. Or you can do the same thing like in the BERT language model, that you have kind of all this information here, and you just do not, you mask out this information in the middle and set it to 0, how this is here done, and then you try to like predict what is in between. So this is kind of what has been done in the BERT model, where they try to predict the word in between in a sentence. So if I have a sentence, and you just remove one word in between and try to predict that token. Okay, let's quickly look into some benchmarks. We have here different scores, and we first of all look into these two here, the min ADE and the min FDE. The min ADE stands for minimum average displacement error. You can't think of that like that you have a ground truth trajectory, which from a car. So this is the trajectory. A car gets faster and faster. That's why the distances get bigger here, for example. And your predictor kind of predicts different scenarios. It, for example, predicts something like that it takes a turn, does a lane change, or really just hits the ground truth. That means it looks like that here in red, and here they average the L2 loss between all these predictions, which are closest, so the red and the green one. Okay, and then we have the min FDE. So instead of like averaging each time step, they just look at the final displacement. That means they just look at the final displacement error, which is then also the L2 distance here. The next one is the miss rate. So the formula for the miss rate goes like that. I have the false negatives, the amount of false negatives divided by the sum of the false negatives plus the true positives, and they look at the final endpoint and the prediction if they are within a radius of 2 meters. So if the predictions are within the radius of 2 meters from the ground truth, and if they are inside, they are counted as true positives, and if they are outside, they are counted as false negatives. And here we see that they also perform very well. Last but not least, we have here the mean average precision, which is nothing more than the precision recall curve, but that we get the sum under the curve. So precision is nothing more than the true positive divided by the true positive plus the false positive. That means all cars I detect versus the falsely detected ones. And the recall is the true positive divided by the true positive plus the false negative. So all those which are not detected. So, and to generate this sweep, this curve, one has to sweep over the confidence from here to there. So here we accept, at that point, we accept lower confidences, and here higher confidences. And something might, as I'm not sure here, but I'm quite sure that also within 2 meters, something is called as true positive. Especially in that score, they do not beat another detector, but still they perform on the other benchmarks very good, very well. Let's have to the end a last qualitative view on some data, but here we look into the goal condition prediction to navigate the self-driving car or autonomous vehicle to a selected goal position. So let's have a look into these cherry-picked scenarios. Therefore, we start with A. What we can see here are such a rasterized image of the behavior situation. You can see in these round dots are predicted, so these circles are predicted trajectories of different vehicles. The vehicles are these squares, and you also can see the road graph. For example, so lines are a road graph. So this is kind of the street boundaries. And also not here, but in other scenes you can see kind of traffic lights, which are also just lines with a specific color. And here, for this situation, we have a goal. Here, this star is set to here. That means our vehicle here in white is staying here on this lane, while we also predict then the behavior of this vehicle which is close to us, and it also stays in the lane. But then they make the example what can happen, or what the predictor will say if we plan to do a lane change here. So as we can see, is that the predictor is indicating a lane change. So we start at that lane and move to that lane. And while this is happening, the blue car, at least that's what the predictor predicts as one possible future, is that this car, kind of moves closer to a little bit more to the left. So here it stays more on the right, and then it moves a little bit more on the left. Okay, this is situation number 1. Then we'll look into situation number 2. So this scenario B looks like that we have our car here. And here we can, by the way, see some of these features. I'm not sure if you can see the video, but here you can see like road graphs. Here's some kind of maybe traffic light or traffic sign which somehow explains which traffic rules have to be applied for this current situation. Okay, so in this situation, the ego vehicle, or for which we would like to set a goal, we're gonna tell this car to just stay. So it just takes a long time to make this little move, and this kind of indicates for that vehicle that it can pass there. This is the one situation. So in the other behavior situation, since this is a very narrow space here, so this is the space where the street actually is, we're going to go through the situations but make some space for this agent here, so that it can move and can move forward to there. Then we have another situation where we have, so here we can see that this vehicle is instructed to follow this lane here until there, and the predictor is predicting each of these steps while also predicting these steps of that vehicle. In another scenario, or within another goal, kind of, this vehicle is instructed to turn at that intersection to there, and that's also what we can see here. And also we can see that here it's kind of faster, and here these circles come closer, so it's kind of being slower here. But then again, we see here, by the way, that these circles get again, the distances get again a little bit bigger. So this is maybe a sign that it's also accelerating again once more. So that's it. I hope I could give you a rough overview of this great paper. If you want to know more about it, I highly recommend that you read it yourself. I hope you enjoyed the video. Stay tuned. Bye.